Something is stopping us from reaching the stars. Not distance, not time, nor the rockets we have or the ones we might build. Something deeper. There is a speed the universe will not let us cross. Light reaches it. Nothing with mass ever has or ever will. And the closer anything gets to that boundary, the harder the universe pushes back, as if the laws of physics themselves are holding a door shut. Now most people hear that and think, engineering problem. Give it time, give it energy. We broke the sound barrier. We will break this one too. But this barrier is not made of metal or air or anything we can push through with enough force. It is made of space-time itself. And by the end of this video, you are going to understand exactly why this limit exists, why it cannot be moved by any engine ever built, and what it tells us about the kind of universe we actually live in. If you enjoy exploring questions like this with us, subscribing helps others find them too. Sharing the video helps even more. Let's begin. The public version of this topic usually begins with a very simple frustration. We look out at the stars, realize the nearest one is more than 4 light-years away, then hear that nothing with mass can travel at light speed, let alone beyond it. That feels almost insulting. The universe is unimaginably vast, and then physics seems to tell us we are not allowed to cross it quickly. That frustration is reasonable, but it often pushes the conversation into a weaker form. People ask, why is light the fastest thing? Why can photons do something spacecraft cannot? Why can we not simply build a more powerful propulsion system? And underneath those questions sits an assumption that usually goes unnoticed. It assumes the speed of light limit is like the top speed of an engine. If a car cannot exceed a certain speed, we look to horsepower, drag, tire quality, or stability. If a plane struggles to go faster, we ask about heat, materials, combustion, and control surfaces. Those are engineering ceilings. They can be raised, sometimes dramatically, but the light speed limit does not behave like that. Physics does not present it as the current best performance of a particularly impressive object. It presents it as a universal limit showing up in the rules themselves. That difference matters. One kind of limit says, this machine is not good enough. The other kind says, reality is organized in a way that constrains what counts as physically meaningful motion and influence. We can feel how unusual that is by comparing it with other hard problems. Mountains are difficult to cross, but they are not absolute barriers. Gravity is powerful, but it can be worked against. Even escape velocity is not a universal prohibition. It is a threshold that can be met with enough speed. When humans encounter difficulty, our standard response is to add energy, intelligence, and better technique. And that same instinct is why many people hear the phrase, nothing can go faster than light, and immediately ask, what if we just add more energy? If speed is a quantity, then why should it stop at a particular value? Why should nature care? The answer is that nature does not care in the human rule-making sense. It is not enforcing a policy. The speed limit exists because the world is not built the way everyday intuition suggests. We live as though space is one thing, time is another, and speeds are merely ratios between them. But at a deeper level, relativity says the relationship between space and time is itself structured by an invariant speed. That word invariant is the key. The value c, the vacuum speed of light, is not just another measured speed like the speed of a bullet or a probe. It is the same for all inertial observers. Once that fact is taken seriously, it changes not just how fast things move, but how time and distance are measured at all. And this is why the common slogan, nothing can go faster than light, is both useful and misleading. It is useful because it points toward a real limit. It is misleading because it makes it sound as though light happened to win a race. It suggests photons are exceptional racers, and everything else is just too slow to catch them. That picture is backwards. The deeper truth is that relativity contains an invariant causal speed, and light in vacuum travels at that speed. Light matters because it reveals the structure, not because it created it. And that shift in emphasis changes the whole topic. Once you stop asking why a spacecraft cannot beat a photon and start asking why the universe has an invariant causal speed, you are no longer discussing propulsion alone. You are discussing simultaneity, causality, and the geometry of space-time. Now, a useful way to see this is to notice that the speed limit appears in places that have nothing to do with rockets. It appears in how electromagnetic waves propagate in vacuum. It appears in how different observers relate measurements of time and distance. It appears in the structure of relativistic energy and momentum. It appears in the cone-shaped boundary separating what can influence an event from what cannot. The same constant keeps returning because it is not an accident tied to one phenomenon. It is embedded in the framework, and that is why the real puzzle is not why humans are bad at building fast spacecraft. The real puzzle is why reality has a universal speed built into it at all. The answer will force us to give up something people once took for granted: the idea that time is absolute and that the universe contains a single global now. Once that goes, the speed of light limit stops looking like an arbitrary cap and starts looking like the organizing line of causality itself. Before we get there, it helps to be clear on one point. Asking whether we can go faster than light is not a stupid question. It is exactly the right question if it leads to the deeper issue. But if the question remains at the level of stronger engines and bigger fuel tanks, it misses the reason the limit is interesting. The interesting part is not that c is hard to reach. The interesting part is that c is woven into the definition of how events in space-time can be connected. Now, to see why this is so radical, start with the world as Newton would have imagined it. In classical physics, space and time are separate and absolute. Space is a stage on which objects move. Time flows the same way for everyone, regardless of where they are or how they travel. If two people are moving relative to one another, they may disagree about the speed of an object, but they agree on the same universal clock and the same idea of simultaneity. That picture works extremely well in ordinary life. If a train moves at 50 km per hour and a passenger walks forward at 5 km per hour relative to the train, someone standing on the ground says the passenger is moving at 55. Velocities add. The arithmetic is familiar. It feels like common sense because at everyday speeds it describes reality well enough. Now imagine doing the same thing with light. A flashlight on a moving train emits a beam forward. Classical intuition says someone on the train should measure the beam at light speed, while someone on the ground should measure the beam at light speed plus the train's speed. Different observers should get different values because their motions differ, but nature refuses to cooperate with that expectation. In vacuum, every inertial observer measures the same value for c, not approximately the same, not close enough to pass a sloppy test. The same, that empirical and theoretical fact, sits at the heart of special relativity. The temptation is to hear that and think light must be doing something bizarre. But the deeper reading is that our original assumptions about space and time were too crude. If the laws of physics are to have the same form in every inertial frame, and if c is to come out the same for all inertial observers, then some part of the old Newtonian structure has to break, and what breaks is not c. What breaks is the idea that time and distance are absolute in the old sense. And this is the point where many explanations become muddy. They say relativity is weird, time bends, everything gets strange, and then they move on. But the logic is actually cleaner than that. Suppose two observers move relative to each other. If they both have to measure light in vacuum at the same speed, then they cannot both preserve the same Newtonian bookkeeping for lengths and durations. Their measurements of space and time must shift in such a way that the invariant speed remains invariant, and that is the heart of the matter. Relativity does not begin by making time flexible for dramatic effect. It begins by taking the invariant speed seriously. The rest follows, and this is why c is more than a convenient number. It is built into the conversion between spatial and temporal components in spacetime. It enters the Lorentz transformations, the mathematical rules connecting one inertial frame to another. It also appears in the equations governing fields and particles. The same constant shows up again and again because the theory is organized around it, and a particularly important clarification belongs here. The universe did not first decide that light is special and then build all physics around that choice. Rather, relativity contains an invariant speed as part of its structure, and light in vacuum travels at that speed. Light is therefore the clean physical phenomenon that reveals the deeper rule, and that matters because otherwise the topic becomes confused. If you say the speed limit is the speed of light because light is special, you make it sound accidental. If instead you say light in vacuum moves at c because c is the invariant causal speed built into spacetime, then light becomes evidence of the structure rather than the source of it. You can hear the difference in how the question changes. The weaker question is, why is light special? The stronger question is, why does spacetime contain an invariant speed that light in vacuum happens to trace? That stronger question also explains why C governs more than optics. It matters for electromagnetic waves, yes, but also for causality, energy-momentum relations, particle kinematics, and the way events are ordered across frames. The speed of light limit is therefore a symptom of something deeper. The real issue is the existence of a universal invariant causal speed. And another useful point is that C is not best thought of as just a large velocity. In relativity, it acts partly like a unit conversion factor linking temporal and spatial measurements. That is one reason it appears so naturally when time and distance are combined into spacetime intervals. The theory is telling us that space and time are not independent containers. They are parts of a single structure whose relationships are constrained by C. And once you understand that, the topic stops being a narrow question about fast things. It becomes a question about the shape of reality. Why do different observers, all doing valid physics, have to agree on the same causal speed? Because the laws are not written on top of absolute Newtonian space and time. They are written into a relativistic space-time whose structure already includes that invariant speed. And once that is true, the next sacrifice becomes unavoidable. If everyone agrees on C, they cannot all agree on what counts as simultaneous. The hardest step in understanding the speed of light limit is not accepting that c is constant. It is accepting what that constancy forces us to abandon. For most of human life, the idea of a universal now felt obvious. Maybe two people were far apart. Maybe signals took time to travel. Maybe clocks had to be synchronized carefully. But surely there was still one correct answer to the question, what is happening right now across the universe? Surely the disagreements were just practical inconveniences. Now, special relativity says that intuition does not survive. There is no frame-independent global present in the Newtonian sense. Simultaneity depends on the observer's state of motion. The famous train and lightning thought experiment remains valuable because it shows this with minimal machinery. Imagine a long train moving steadily past an embankment. Lightning strikes both ends of the train. An observer standing midway between the strike points on the embankment receives the two flashes at the same moment and concludes the strikes were simultaneous. Now consider an observer sitting at the midpoint of the moving train. While the light from the two ends is traveling inward, the train observer moves toward the flash coming from the front and away from the flash coming from the rear. If the speed of light is c in both directions for that observer as well, the flashes cannot arrive together. The train observer concludes the strikes were not simultaneous, but there is no cheat here. Neither observer is making an error that relativity later corrects by pointing to the other one as secretly right. The disagreement is real because simultaneity is not absolute. Events simultaneous in one frame need not be simultaneous in another moving frame. And that result is so far from common intuition that people often try to downgrade it into an illusion. Maybe it is just about who saw the flashes first. But the whole point is that relativity is not talking about delayed perception alone. It is talking about the correct assignment of times within each inertial frame once the constancy of c is respected. And this is the conceptual hinge of the entire subject. If you insist that every inertial observer measures the same c, then observers must disagree about time intervals, distances, and simultaneity in precisely the way the Lorentz transformations require. Time dilation and length contraction now come into view, but they need to be framed carefully. They are not decorative side effects. They are part of the bookkeeping system that makes the invariant speed possible for all observers. They are not the cause of the speed limit. They are consequences of the same structure, and this is one of the most important discipline points in this whole topic. It is easy to say, as objects move faster their time slows down, therefore they cannot reach light speed. That reverses the logic. Time dilation does happen, but it is not an ad hoc mechanism the universe switches on to stop fast travel. Time dilation, length contraction, and the relativity of simultaneity All arise, because space-time must be described in a way that preserves the same C for everyone. Now, a useful image is to think of different observers slicing space-time differently. In Newtonian physics, everyone slices the world into the same layers of now. In relativity, those slices tilt depending on the observer's motion. What one observer calls simultaneous, another may divide into before and after. That sounds disturbing, but it is not chaos. There is still a deeper invariant structure underneath those different descriptions. The space-time interval between events and the causal relationships allowed by light cones provide stability. Observers may disagree on the coordinates assigned to events, but not on the underlying relativistic framework. And this is also why the relativity of simultaneity is not an optional extra that can be ignored if we only care about the speed limit. Without it, the causal role of C becomes much harder to understand. The reason faster-than-light signaling causes trouble is not merely that it is very fast. It is that in a universe with relative simultaneity, a signal outside the light cone can flip the order of connected events for some observers. Before we reach that consequence, let us sit with the philosophical shift for a moment. Special relativity does not just say clocks behave oddly when they move quickly. It says the universe does not come pre-divided into one objective universal timeline for all distant events. Motion changes how events are grouped into space and time. That is far deeper than a statement about fast rockets. And it also explains why the old question, why can't we just keep speeding up, is incomplete. Speed itself is defined against space and time. If space and time are observer-dependent in the relativistic way, then speed cannot be treated as a simple quantity floating on top of an absolute background. The closer we look, the more the speed limit turns out to be built into the geometry of description itself. Preserving C requires the restructuring of temporal order. And once temporal order stops being universal for distant space-like separated events, the next issue becomes unavoidable. What then keeps causes and effects from becoming scrambled? The answer is the light cone. Because relativity of simultaneity is the hinge between invariant speed and causal structure, it is worth slowing down and making it feel more concrete. Imagine two clocks placed far apart in otherwise empty space. In one chosen inertial frame, we synchronize them carefully using light signals and standard Einstein synchronization. In that frame, the clocks are synchronized by definition and by procedure. When one clock reads noon, so does the other. Now imagine a second observer passing by at high speed. This observer is not required to agree that the two distant clocks are synchronized. In fact, special relativity says that the moving observer generally will not agree. The observer will attribute different time readings to those two distant locations once their own frame synchronization rules are applied. That sounds like mere bookkeeping until you see what it means. It means there is no frame-neutral answer to the question, what time is it right now over there for a distant location? The answer depends on the observer's inertial frame. This is difficult because our brains are trained by slow speeds and short distances. In ordinary life, disagreements of this kind are so tiny they vanish beneath daily experience. The world feels globally synchronized, not because it truly is in the Newtonian sense, but because relativistic differences at human speeds are usually negligible. Yet once you accept that distant simultaneity is frame-dependent, the rest of the subject becomes much less mysterious. Time dilation stops looking like a weird punishment for moving clocks. Length contraction stops looking like a magical physical squeeze. They become part of one consistent adjustment in how space-time measurements work across frames. Now, a useful way to picture this is to imagine each observer laying down a grid on space-time. Their grid lines of equal time are not universal. Relative motion tilts them. Each observer still does valid physics, still measures the same C, and still agrees on the invariant causal structure. But they no longer share one cosmic sheet of simultaneous events. This matters for the speed limit, because a faster-than-light signal would connect events that live outside the light cone, precisely where frame-dependent orderings are allowed. Inside the cone, everyone is constrained enough to preserve causal order. Outside the cone, that protection is gone. So the relativity of simultaneity is not a side note for advanced students. It is the exact reason the light speed limit carries causal force. If time were absolute, the story would be different. But once simultaneity becomes relative, c stops being just a speed and becomes the boundary that keeps cause and effect from becoming observer-dependent in a destructive way. Worth noticing what relativity is not saying. It is not saying all order is subjective. It is not saying reality dissolves into perspective. It is saying some temporal relationships are frame-dependent, specifically for events outside one another's light cones, while causal order for connectable events remains protected. And that balance is what makes the theory so powerful. It preserves objectivity where causality requires it, while surrendering absolutism where nature does not support it. If we want the shortest version, it is this: the universe does not offer one absolute now for distant places. It offers one invariant causal structure instead. That trade is the beginning of the speed limit story. Time dilation and length contraction are among the most famous consequences of relativity, but they are also among the most abused. They are often presented like special effects, as though motion causes clocks to mysteriously run badly and rulers to behave strangely, and that framing is easy to remember and easy to misuse. It suggests ordinary reality is being distorted by speed. The more accurate framing is that space-time measurements differ across inertial frames in lawful ways, because the invariant speed c must be preserved. Take time dilation first. If two observers move relative to one another, each can regard the other's clock as running differently under the correct comparison conditions. This is not a paradox once simultaneity is understood, because the observers are not sharing one universal slice of now against which all distant clock readings are compared. Their frame-dependent synchronization structures matter, and likewise, length contraction is not an object internally deciding to compress itself out of embarrassment for moving quickly. It is a statement about how spatial extension is measured in frames that do not agree on simultaneity. To measure the length of a moving object, you need positions of its endpoints at the same time in your frame. Another observer moving relative to you does not share the same definition of same time for distant endpoints. So the resulting length assignment differs, and that is why these effects belong in the same family as the speed limit. They are not random companion phenomena. They are all consequences of replacing Newtonian absolutes with relativistic structure. And that matters because weak explanations often make time dilation sound like the reason objects cannot reach light speed. But time dilation is not the enforcement mechanism. It is one visible feature of the same geometry, whose deeper enforcement shows up in the light cone boundary and the diverging energy cost for massive motion near C. And a more useful way to summarize the situation is this: the universe does not distort time in order to stop fast travel. Rather, the universe has an invariant causal speed, and the consistent description of space and time in such a universe necessarily includes time dilation, length contraction, and relative simultaneity, and that framing preserves the logic. First comes invariant speed, then comes the restructuring of measurement, then comes the causal and energetic meaning of the boundary. And there is a practical advantage to getting this right. Once time dilation is treated as part of the same structure rather than as an isolated curiosity, the whole theory feels less like a collection of weird exceptions and more like one coherent map. And that coherence is exactly what gives the speed limit its authority. Take any event in space-time. It could be something dramatic, like a supernova, or something ordinary, like the instant you press a button. From that event, light can spread outward in all directions. If you draw space horizontally and time vertically, the expanding front of those light signals traces out a cone. The upward cone is called the future light cone. It marks the set of events that can be reached from the original event by a signal moving at exactly c. Events inside that cone can be reached by slower than light motion or influence. The cone is therefore not just a picture of light, it is a map of possible future causal reach. And there is also a downward cone, the past light cone. It contains all the events from which light or slower causal influence could have reached the event in question. Everything inside or on the past light cone could, in principle, have contributed to what happened there. Then there is the region outside both cones. Those are events too far separated in space relative to the available time. No ordinary signal traveling at or below c can connect them. In relativity, those separations are space-like. And this is the point where the speed of light limit stops looking like a random law and starts looking like geometry. The light cone is a boundary between what can causally matter and what cannot. It tells you whether an influence is possible at all, not just whether it is technologically convenient. If an event lies inside your future light cone, you can in principle affect it by sending some subluminal signal or by physically traveling there slower than light. If it lies exactly on the cone, only a light-like or massless signal can connect the events. If it lies outside the cone, no ordinary causal path exists between them within that interval. That gives c a very different flavor from everyday maximum speeds. A race car has a top speed because of engineering and friction. The cone boundary is not an engineering limit. It is the line separating causally connected spacetime from space-like separated spacetime. We can think of the light cone as the local architecture of possibility. It tells you which parts of the universe can still talk to each other and when. It tells you what counts as future, what counts as past, and which distant events are simply not within causal reach under ordinary relativistic rules. And this also shows why light matters so much. Light in vacuum traces the cone boundary. That does not mean the boundary belongs to light in a merely material sense. It means light is the familiar phenomenon that runs exactly along the edge between time-like reachability and space-like separation. Now, a good way to make this intuitive is to imagine an event as the center of an expanding sphere of possible influence. At 1 second after the event, only places within 1 light second can have been affected. At 2 seconds, the sphere is larger. Over time, this expanding sphere becomes the cone in spacetime. The edge of the sphere is where light sits. The interior is where anything slower must live. And now we have a picture we can work with. Now notice what this does to the question of communication. If information could be transmitted instantly, the cone would collapse into something very different. Distant places could be updated with no delay, and the distinction between inside and outside the cone would evaporate. But relativity says there is a finite speed of influence. That is why communication delays across space are not accidents. They are the practical face of causal structure. The cone picture is also powerful, and we can use it to organize what different observers may disagree about. For events inside one another's light cones, everyone must agree on their causal order. They can disagree about elapsed durations or about coordinates, but not about which event could have caused which. For events outside one another's cones, different observers can disagree about temporal order precisely because no causal connection is available under the ordinary rules. And that last point is often underappreciated. The relativity of simultaneity would be much less interesting if the cone structure did not tell us which disagreements are harmless and which would be catastrophic. If two distant, causally disconnected events trade order between frames, nothing breaks. But if a genuine cause-effect pair were allowed to move outside the cone, then those frame-dependent reversals would stop being harmless. And that is why light cones are not just diagrams used in textbooks. They are the clearest expression of what the invariant speed is doing. They show that c is the boundary of causal propagation. The cone picture also prepares us for one of the cleanest answers to the photon versus matter question. Massless particles travel on the cone boundary. Massive objects follow paths strictly inside the cone. They can lean toward the boundary as their speed rises, but they do not ride the boundary itself. That difference is not decorative. It is the line between the two categories of motion relativity allows. Understanding it will help us avoid one of the most common mistakes in popular explanations, which is to say that photons go at c simply because they have no mass and then leave it there. The real story is sharper. Massless propagation is tied to the null boundary of spacetime itself, and before we explain that more carefully, we need to see why leaving the cone would not merely mean going very fast. It would mean undermining causal order. Now, people often remember the number 299,792,458 meters per second and think the topic is fundamentally about a giant velocity value, but the number by itself is not the interesting part. The interesting part is what role that value plays. Imagine a universe where some maximum speed existed for practical reasons, but did not define causal structure. That would be a very different kind of universe. It might limit engineering, but it would not force a reorganization of simultaneity. It would not necessarily define a universal cone separating the causally reachable from the unreachable. It would not necessarily show up across field theory, kinematics, and frame transformations. Now, in our universe, C does all of those things. That is why the number matters. It is not large merely in a numerical sense. It is structurally privileged, and this is also why the phrase speed of light can both help and hinder understanding. It helps because light in vacuum is the most familiar thing that travels at sea. It hinders because it can make the topic sound as if the rule belongs first to optics and only secondarily to everything else. The better framing is the other way around. The rule belongs first to spacetime and causality. Optics is one of the places where it becomes visible. That distinction may seem subtle, but it cleans up a lot of confusion. It explains why people get misled by light slowing in glass or water. In a medium, the effective propagation speed of light can be reduced by interactions with matter. But that does not mean the deeper relativistic benchmark has changed. The invariant vacuum speed c remains the structural constant relevant to causal cones, and it also explains why massless particles beyond photons still fit the same story. The issue is not the visible phenomenon of light alone. The issue is null propagation in a relativistic spacetime. Thinking in terms of the cone boundary rather than the headline number also improves intuition about travel. If a spaceship could somehow cross the numerical value c while still remaining an ordinary massive object in special relativity, it would not merely be beating a record. It would be crossing from one causal category into another. That is why the language of faster and slower is too weak on its own. The stronger language is inside the cone, on the cone, or outside the cone. Once you adopt that language, many public confusions dissolve. A particle accelerator pushing protons ever closer to C is not trying and failing to hit a high score. It is pushing a time-like trajectory ever closer to the null boundary. A deep space communication delay is not just a slow message. It is what it looks like when information must travel within causal structure. A spacecraft benchmark is not just a small fraction of a big number. It is evidence of how far human engineering still is from the boundary regime. So yes, C is a number. But in this topic, the number is the least important part. What matters is that it is the invariant speed defining the edge of causal reach. And another useful cleanup is to notice that the speed limit applies more broadly than material travel. The deeper rule concerns signals, influence, and causal propagation. And that matters because people sometimes hear nothing with mass can reach light speed and quietly imagine a loophole. Perhaps matter is restricted, but information might not be. Perhaps a signal could outrun the object carrying it. But in relativity, the causal boundary is not merely about spacecraft hulls. It is about what can transmit influence from one event to another. And that is why the phrase speed of causality, used carefully, captures something important. The limit does not only govern how fast matter moves, it governs how fast the consequences of one event can become available elsewhere. So, seen this way, the light speed limit touches almost every part of physical explanation. Radiation, communication, interaction, measurement and control all live within it. A universe with a different causal speed or no invariant causal speed at all would not just have faster travel, it would have a different architecture of explanation. And one subtle but powerful aspect of relativity is that the light cone structure is local to every event and yet universal in form. Every event carries its own past and future cone. The cones are not imposed from one central cosmic source. They arise everywhere. That helps explain why the limit feels so deeply built in. It is not a rule you encounter only on long interstellar routes. It is present in every local interaction. Every emission, every detection, every exchange of cause and effect unfolds inside a local cone structure. But at the same time, the form of that structure is universal. Different observers, different places, different experiments, all inherit the same invariant causal speed in vacuum. That combination of locality and universality is one reason the theory feels so robust. The rule is not provincial. It is woven into the local grammar of events everywhere. Here is the deepest reason the speed limit matters. It is not merely that faster-than-light travel would shorten journeys. It is that in a universe with relative simultaneity, allowing influence outside the light cone destabilizes the ordering of cause and effect. The light cone already tells us something crucial. If event B lies inside the future light cone of event A, then A can in principle influence B by an ordinary causal path. In that case, all observers, whatever else they disagree about, must preserve the ordering strongly enough that B does not become the cause of A. Causal order is stable inside the cone, but for events outside the cone, the situation is different. Since no ordinary influence can connect them, relativity permits different inertial observers to disagree about which event happened first. One frame may place A before B, another may place B before A. That is not a contradiction because the events are space-like separated and cannot normally stand in a cause-effect relation. Now imagine a signal that outruns C. Suppose A sends a message to B along a path outside the cone. In one observer's frame, A may send the message and B may receive it later. But because the interval is space-like, another observer moving relative to the first can assign the events the opposite order. In that frame, B receives the message before A sends it. Even this first step is enough to show us that faster-than-light influence does not fit comfortably into relativity. The moment you connect space-like separated events with a real signal, the frame-dependent reversals of order stop being harmless bookkeeping differences and start touching causal meaning. And if you allow such signaling in both directions between appropriately moving observers, the trouble deepens. It becomes possible to build a sequence in which a reply arrives back at the original sender before the initial message was sent in that sender's own frame. In other words, faster-than-light signaling opens the door to causal loops. We do not need to build a full science fiction paradox to appreciate the problem. The core point is already enough for us. In a relativistic universe, simultaneity is relative. Therefore, any signal that links events outside one another's light cones can be ordered differently by different observers. That is why C is not merely a speed cap, it is the speed that keeps the causal skeleton of spacetime intact. And this is also why popular treatments often become misleading when they say faster-than-light travel would mean time travel, full stop. That line compresses several layers of reasoning into a slogan. The more careful version is that in a spacetime with relative simultaneity, superluminal signaling generically allows frame orderings that can be arranged into causal contradictions. The real issue is not cinematic time travel imagery. The real issue is causal instability, and it helps to see why relativity can tolerate some disagreements and not others. If two distant stars explode independently and are outside each other's light cones, observers may disagree on which explosion occurred first. That is acceptable because neither explosion caused the other. No contradiction appears. But if one explosion somehow sent a faster-than-light trigger that caused the other, then different observers could disagree about whether the cause preceded the effect. Now the disagreement is not harmless, it attacks the consistency of explanation itself. That is the elegance of the speed limit. It does not exist as a police rule against high performance. It exists because once C is invariant and simultaneity is relative, anything that outruns the cone boundary threatens to turn causality into something observer-dependent in a destructive way. And this is also why the phrase "the speed of causality" is useful, so long as it is handled carefully. It does not mean visible light is somehow mystically in charge of cause and effect. It means the invariant vacuum speed c defines the boundary along which causal influence can propagate. Light in vacuum happens to trace that boundary, so light becomes the familiar messenger of the deeper rule. And at this point the topic often becomes emotionally clearer. The universe is not saying you are allowed to go very fast, but not that fast. It is saying something stronger and more structural. It is saying there is a finite cone of possible influence attached to every event, and coherent causal order depends on respecting that cone. So if you ask why the speed limit exists, the answer is not merely because acceleration gets hard. It exists because the universe is relativistic, not Newtonian, and in that relativistic structure, faster-than-light influence would wreck the distinction between before and after for connected events. Only now, after that causal story is in place, are we ready to answer the question about photons and matter that we started with. Why do some things live on the cone boundary while everything with mass remains inside it? Now, to make all of this feel less abstract, imagine two research stations drifting far apart in deep space. Call them Station A and Station B. They have synchronized their procedures, they know their relative motion, and each carries clocks and detectors of exquisite precision. Let's say Station A sends an ordinary light speed signal to Station B. Everyone agrees on the essential causal structure. The message leaves A, traverses the separation, and reaches B. Different observers may disagree on durations and frame coordinates, but nobody gets to say the receipt caused the emission. The signal remained on or inside the relevant light cone. Now let's imagine, just for argument, that A can send a faster-than-light pulse instead. In A's frame, perhaps the story still looks innocent. A transmits, then B receives shortly afterward. Mission accomplished. But because the transmission lies outside the light cone, there exist other inertial frames in which B receives the pulse before A sends it. If B is also allowed to reply superluminally while moving relative to A in the right way, the return signal can be arranged to land back at A before the original transmission event in A's own frame. And what matters here is not the cinematic thrill of receiving tomorrow's mail today. What matters is the failure of causal order to remain stable across the theory. Ordinary relativity protects causal links by keeping real influence inside or on the cone. Superluminal signaling breaks that protection. This thought experiment is powerful because nothing about it depends on giant starships or speculative machinery. The problem appears as soon as you combine three ingredients: an invariant speed, the relativity of simultaneity, and influence outside the light cone. Together they generate causal trouble, and that is why the speed limit should be heard less as a transportation rule and more as a consistency condition. It keeps all of us inside one coherent causal world, even when they disagree about many details of measurement. And one final subtle point is worth making. The phrase faster than light sounds as though light is the reference competitor and everything else is measured against it. That wording is convenient, but not quite ideal, and what we really mean is beyond the invariant causal speed c. Light in vacuum is simply the familiar phenomenon that moves at c, so its name becomes shorthand for the deeper boundary. But in explanatory terms, the real contrast is not light versus non-light. It is null causal propagation versus time-like massive motion. Why does that matter? Because wording shapes intuition. If you say faster than light too many times without explanation, the audience can accidentally build the wrong model. They start thinking about a substance called light as if it were setting the pace in a race. The better model is that space-time has a causal boundary, and light in vacuum traces that boundary. And once that is clear, many questions become easier to answer. Why does causality care about c? Because c is the cone boundary. Why do photons travel at c? Because they are massless excitations on null trajectories. Why do massive objects stay below c? Because their world lines are time-like and do not become null while remaining massive. Why is the energy cost so punishing near c? Because pushing time-like motion toward the null boundary runs into the asymptotic structure of relativistic dynamics. The language of faster than light is therefore acceptable so long as it is constantly translated back into the stronger language of invariant speed and cone structure. Otherwise, the topic slips into a weaker metaphor. Now, when people first learn that nothing with mass can reach the speed of light, the next thought is almost automatic. Then, why can light travel at that speed? What does light have that matter does not? The weakest answer is simply because photons are massless. That statement is true as far as it goes, but by itself it often creates the wrong mental picture. It encourages people to imagine mass as a kind of drag substance, and the absence of mass as a free ticket to move infinitely fast. Relativity is cleaner than that. Here we find the fundamental distinction: two kinds of trajectories in spacetime. Massive objects follow time-like paths, which lie inside the light cone. Massless particles follow null or light-like paths, which lie exactly on the cone boundary. A massive object has a rest frame. However fast it moves relative to you, there is always an inertial frame in which that object is at rest, at least momentarily and locally. That is part of what it means to possess rest mass. In that frame, the object is not racing through space at c. It is simply existing with proper time flowing along its world line. A massless particle is different. There is no inertial rest frame in which a photon is sitting still. The idea of a photon at rest is not just impractical, it is outside the allowed kinematics of special relativity. Massless propagation in vacuum is tied to the null structure of spacetime, the cone boundary itself. And this is why it is better to say massless particles do not merely happen to move at c. The structure of relativity leaves them no slower vacuum option. Meanwhile, anything with rest mass remains inside the cone and therefore below c. And another way to say it is that the cone boundary is not a speed goal matter almost reaches and photons happen to win. It is a distinct class of trajectories. Massive and massless entities do not differ only in how much effort they can exert. They differ in the kind of path spacetime allows them to take. And this is where we can clean up several common misconceptions. First, photons are not special because they are made of pure energy in a mystical sense. They carry energy, certainly, but so do massive particles. Energy is not what makes the difference. The difference is that a photon has zero rest mass, and therefore propagates on a null world line. Second, matter does not fail to reach c because it is somehow too heavy in the everyday sense. A proton is tiny, an electron is even tinier, yet both are massive in the relativistic sense of having non-zero rest mass, and so both follow time-like world lines. A spacecraft and an electron are very different engineering objects, but the same geometric distinction applies to both. Third, saying light is massless does not mean the deeper topic is finished. The crucial question is why masslessness corresponds to motion at c in vacuum. The answer is that c is the invariant causal speed built into the geometry, and massless excitations propagate along the null boundary of that geometry. It helps to imagine, and let us do this carefully, the light cone not as a wall, but as a category boundary. Inside the cone lives everything that can have a rest frame and proper time along a time-like path. On the cone lives massless propagation, which does not admit a rest frame in the same way. The difference is structural, not motivational, and this is also why brute force cannot solve the problem. We can keep feeding energy into a massive object and drive it closer to the cone boundary. But while it remains a massive object, its path remains time-like. You do not eventually bully it into becoming null motion while preserving its original kinematic category. The cone picture keeps our story honest. Massive objects inhabit the interior. Light-like propagation inhabits the edge. That is why the phrase "nothing with mass can reach c" is more than a slogan. It is a statement about the type of world line available to an object with rest mass. And a deeper benefit of this picture is that it prevents us from telling the story backwards. It is tempting to say photons move at c because they have no mass, and therefore matter cannot keep up. But the sharper version is that relativity contains an invariant null structure. Massless quanta propagate on that null structure, and massive objects propagate within the time-like interior. The geometry comes first, and this also clarifies why slower than light in materials does not threaten the deeper rule. Light can travel more slowly through matter because interactions with the medium change how the electromagnetic disturbance propagates through that material. But the invariant vacuum speed c remains the causal benchmark built into relativity. The cone boundary is defined in vacuum, not by every effective propagation speed in every medium, and once the geometry is clear, the practical question becomes simpler. If massive objects are confined to the cone interior, what happens when we try to push them closer and closer to the edge? That is where the energy wall appears, and another way to understand the limit is to revisit an older intuition and see why relativity outgrew it. Let's imagine trying to chase a beam of light. In a Newtonian world, you might expect that if you accelerated enough, you could gradually reduce the light's speed relative to you. Perhaps eventually it would appear almost frozen, like a slow-moving wavefront drifting nearby. But Maxwell's equations and the empirical structure of electromagnetism do not permit that classical picture. Light in vacuum does not present different inertial observers with different vacuum propagation speeds in the Newtonian way. Instead, the theory forces the relativity of space and time themselves, so that all inertial observers recover the same c. This thought experiment matters because it exposes the wrong picture very directly. The speed limit is not saying you nearly catch up to a light beam in the ordinary sense, and then some force stops you at the last moment. The theory says your whole frame description changes in such a way that the light beam still propagates at c in vacuum, and that is another reason the topic cannot be reduced to a race. If a photon were merely a fast object on a classical stage, then catching up in principle would make sense. But because c is built into the stage itself, the very act of describing motion changes once relative speed becomes significant. The lesson is subtle but decisive, and we should hold it clearly. The limit is not a line painted onto pre-existing Newtonian space and time. The limit is part of what replaces Newtonian space and time. Now we can return to the question most people began with. If a spacecraft or particle is always inside the cone, what happens when we keep adding energy? Why can it get closer to c but never arrive? Now at low speeds, motion behaves in a way common sense expects. Add energy and speed rises. Double your effort and the result changes in a roughly intuitive way. In this regime, Newtonian physics is a very good approximation, but as velocity climbs towards c, the relationship between added energy and added speed stops behaving like everyday experience. The closer a massive object gets to c, the more energy is required for each further increment of speed. The gains become progressively less rewarding. You keep paying more, and the remaining gap shrinks more stubbornly, and this is why the approach to c is often described as asymptotic. You can get closer and closer in principle, but exact arrival is not reached by a massive object within special relativity. The energy requirement diverges as velocity approaches c, and that wording is important. Popular science long used the phrase relativistic mass, saying that objects get heavier as they move faster. There is historical context for that language, but it often creates confusion. It makes it sound as though the object is literally filling up with some ordinary kind of extra heaviness. The cleaner modern phrasing is that the relativistic energy and momentum relations make further acceleration increasingly expensive, with the required energy growing without bound as v approaches c. This is not a minor semantic improvement. It keeps the explanation attached to the real physical structure. The problem is not that the universe sprinkles extra burden onto fast objects out of spite. The problem is that in a relativistic world, a massive time-like trajectory cannot be pushed onto the null boundary with finite energy. Now, particle accelerators make this vivid. Protons in a modern accelerator can move so close to c that the difference is tiny by everyday standards. Yet, however much additional energy is poured in, those particles do not simply cross the boundary and become superluminal. Instead, their energy climbs while their speed inches ever closer to c without reaching it. That is not a technological accident. It is precisely what special relativity says should happen. Accelerators are not evidence that the limit is soft. They are evidence that the asymptotic structure is real, and this is where E equals mc squared usually enters the story, often in a distorted way. The equation is famous enough to be dangerous. It is frequently used as if it were a one-line proof of everything relativistic. It is not, and what the equation does express is the deep link between mass and energy. Rest mass corresponds to energy. More broadly, relativistic physics treats energy, momentum, and rest mass as elements of one connected description. That matters enormously when discussing what happens to fast-moving matter. But E equals mc squared is not the whole explanation for the speed limit. By itself, it does not give you light cones, relativity of simultaneity, or causal order. It supports the energetic side of the story. It does not replace the geometry. The right way to use it here is as a reinforcing idea. Once you understand that spacetime has an invariant causal speed and that massive objects remain inside the cone, then the energy relations tell you what it costs to push massive matter ever closer to the boundary. The cost rises without limit. The equation is part of that broader framework. Now, a helpful analogy is to imagine trying to touch a horizon that keeps receding in the terms that matter. Not because the horizon itself moves, but because your category of motion never becomes the category needed to coincide with it. The closer you get, the more the remaining difference resists finite effort. Of course, analogies have limits. The actual physics is better captured by the asymptote picture. There is no mysterious force field at sea. No cosmic wall suddenly appears. Instead, the equations governing massive motion simply refuse to permit a finite energy crossing. The boundary is not enforced by a shove backward. It is enforced by the structure of the relationship between energy, momentum, and velocity. And this is also why the phrase, "if we just had enough power," is not wrong so much as incomplete. More power absolutely does matter. It is the reason we can approach C more closely. But more power does not alter the asymptotic rule itself. However advanced the engine, a massive object does not stop being massive. Its world line remains timelike. At this point, the two sides of the story can be seen together. Geometrically, C is the boundary of causal structure, the edge of the light cone. Dynamically, for massive objects, approaching that boundary requires unbounded energy. Those are not rival explanations. They are two ways the same relativistic reality presents itself, and that is why it is a mistake to reduce the speed limit to E equals mc squared alone. If you do that, the whole topic sounds like an energy budget issue. It is more than that. The energy wall matters because the object is trying to approach a boundary already written into space-time geometry, and once you see that, you can return to practical spaceflight with the right sense of scale. Human technology is astonishing, but it is still operating very far from the boundary we are talking about. If someone wants proof that the speed limit is not just a statement about primitive spacecraft, particle accelerators provide the clearest grounded example. In a modern accelerator, charged particles can be driven to speeds astonishingly close to c. By everyday standards, they are effectively at light speed already. Yet the closer they get, the more obvious it becomes that crossing the boundary is not a matter of one final shove. Additional energy continues to matter, but the speed increase becomes ever less dramatic. And this is important for two reasons. First, it shows that relativity is not mainly about giant human-scale craft. The same rule applies to electrons, protons, muons, and heavy ions. Second, it demonstrates that the limit is not a technological placeholder waiting to be erased by better engineering. These are some of the most controlled high-energy systems humans have ever built, and they reveal the asymptotic structure exactly where relativity says they should. An accelerator is therefore almost like a machine for humiliating naive intuition. Everyday instinct says, if something is going very fast, more energy should make it go proportionately faster still. Relativity says not near c for a massive particle, and experiment agrees with relativity. And this is also where the distinction between speed and energy becomes especially important. A very high-energy particle in an accelerator may have energy increasing dramatically, while its speed changes only slightly, because it is already so close to c. If you only watch the speedometer, you miss the physics. The system is not doing nothing. It is revealing that energy and speed are no longer linked in the simple Newtonian way. And that lesson generalizes upward. It tells us why any proposal for near-light speed travel with massive matter enters a fundamentally different regime. The issue is not simply fuel abundance. The issue is what a massive world line can and cannot become. Now, particle accelerators also remind us of another subtle point. The speed limit is not only relevant to vast cosmic voyages, it is already built into laboratory physics. The same c that shapes interstellar hopes shapes terrestrial experiments. That continuity is part of what makes the theory so strong. The rule is not reserved for exotic corners of the universe. It is woven through phenomena we can test directly. And at this point, it is worth stepping away from thought experiments and asking a harder question. Is all of this just elegant theory, or does the real world actually behave this way when we measure it carefully? The answer is that relativity is not held up by one famous anecdote. It is supported by a network of experiments and technologies that only make sense because the invariant speed structure is real. Now, one of the earliest clues came from the old failure to detect the kind of ether wind classical physics once encouraged people to expect. If light were simply another wave moving through a preferred medium, then Earth moving through that medium should have changed the measured speed of light depending on direction. That is not what the best experiments found. The more carefully the measurements were made, the less room there was for the old picture of an absolute background medium with ordinary velocity addition. Now, Einstein's 1905 move was not to treat that as an isolated laboratory oddity. It was to ask what spacetime itself must be like if the laws of physics are to look the same in every inertial frame, and if light in vacuum is measured at the same speed by all of them. The power of the theory since then has been that the consequences are not vague. They show up in clocks, particles, accelerators, and the practical engineering of timing. Think about unstable particles called muons, created when high-energy cosmic rays strike the upper atmosphere. In their own frame, muons decay quickly. Classically, many of them should vanish long before reaching detectors on the ground. But many do reach the surface. From the Earth's frame, their moving clocks run slow enough for more of them to survive the journey. From the muon's frame, the atmosphere is length contracted. Different descriptions, same invariant physics. Either way, the observed result fits relativity's restructuring of space and time, not the older Newtonian picture. Now consider precision clocks. Fly an atomic clock on an aircraft, compare it with clocks left on the ground, and the elapsed times do not match exactly. Some of the difference comes from relative motion, some from gravitational effects once general relativity enters the story, but the key point remains. Time is not a universal background that all clocks share automatically. Precise clocks reveal that motion and gravity change elapsed time in measurable operational ways. This becomes even more concrete in satellite navigation. GPS works only because the system continually accounts for relativistic timing corrections. The satellites are moving relative to receivers on Earth, and they are also higher in Earth's gravitational field. If those relativistic offsets were ignored, navigation errors would accumulate rapidly. The system would not gracefully remain a little wrong. It would fail in ways users would notice very quickly. And that practical success matters because it prevents relativity from becoming a purely philosophical topic. The same theory that says there is no universal now also helps your phone and car locate themselves on a rotating planet. The same theory that ties C to causal structure also shows up in how modern timing networks stay synchronized. Now, particle accelerators provide another kind of evidence. They do not merely accelerate matter to impressive speeds, they reveal exactly the asymptotic pattern relativity predicts. As energy rises, particles with rest mass get closer and closer to C, yet never cross the boundary by ordinary acceleration. The theory does not just forbid a result, it correctly describes the observed approach. So when we say the speed limit is structural, that is not a poetic claim, it is a statement backed by experiment after experiment. Not every experiment measures the same thing, but together they support the same world picture. Light's vacuum speed is invariant. Space and time are not absolute in the Newtonian sense. Causal structure has a finite boundary, and matter behaves accordingly. And this is also why the subject deserves precision in popular explanation. If relativity were only a speculative mathematical framework, there would be more room to treat its claims as optional interpretations. But the reason the theory has authority is that its strange claims keep being cashed out in observation. Muons live longer than naive classical reasoning says they should. Clocks drift in the relativistic way. Navigation systems need the corrections. High-energy particles approach C without crossing it. The experiments do not merely confirm isolated tricks, they confirm the chain, and that matters because the speed limit can sound suspiciously like a slogan until you realize how many corners of reality quietly depend on it. Once you do, the limit stops feeling like a dramatic line from science fiction and starts feeling like a measured property of the world. Now, relativity can feel abstract until you compare it with the machines humans actually build. By ordinary standards, our fastest spacecraft are extraordinary. They leave Earth, survive planetary flybys, and move at speeds that would have seemed absurd not long ago. Now, a strong grounding example is the Parker Solar Probe. At peak speed, it has reached roughly 430,000 miles per hour, about 692,000 kilometers per hour. That is an astonishing engineering achievement. It moves faster than any human-made object has before. But the very reason Parker is a useful example is that it shows both sides of the story at once. On the one hand, human engineering can push far beyond everyday intuition. On the other hand, even our most extreme spacecraft remain tiny fractions of C. Light in vacuum travels about 299,792 kilometers every second. Parker's record speed is extraordinary by human standards and still nowhere near the relativistic boundary, and this is why the gap between current spaceflight and near light speed travel is not just a bigger version of earlier engineering gaps. It is not merely the difference between propeller planes and jets, or jets and rockets. It is the difference between the regime where Newtonian thinking works well enough and the regime where the deeper structure of spacetime becomes operationally unavoidable. At low fractions of c, ordinary mechanics is a practical guide. At substantial fractions of c, you are negotiating with time dilation, relativistic momentum, and the steepening energy cost of every additional speed gain. That is a different world. The same is true for communication. When missions operate across the solar system, engineers plan around signal delay. A command sent to Mars is not received instantly. A data stream from deep space does not arrive the moment it is emitted. These are not logistical annoyances caused by poor engineering. They are examples of a universe in which information itself is constrained by c. And that matters because it ties the abstract physics back to human experience. The speed limit does not only constrain heroic starships in speculative futures, it already shapes real mission planning, real communication lag, and real navigation decisions. Every deep space probe is operating within the same causal framework the light cone describes, and this is also why one should be careful with benchmarks. Spacecraft records do not prove relativity by themselves. They are illustrations, not foundations. Their role is to make scale emotionally legible. They tell us that even the fastest machines we have built are still far from the regime where the final asymptotic climb towards c dominates everything. Now, particle accelerators offer another grounding contrast. There, tiny particles are driven much closer to c than spacecraft ever will be. Yet that success does not weaken the limit. It shows the same rule from a different angle. You can approach the boundary extremely closely, but the final crossing does not occur. Worth noticing how often public discussion confuses the issue by mixing up high speed with relativistic significance. A spacecraft can be extremely fast in human terms and still be deeply non-relativistic in physical terms. Conversely, a particle can be tiny and yet require a fully relativistic description because it is moving close enough to c. The relevant question is not whether something feels fast to us, but how it compares with the invariant causal speed. And once you grasp that, the emotional meaning of cosmic distance changes. The stars are not only far in some neutral geometric sense, they are far in a universe where no ordinary message or vehicle can erase delay by outrunning causality. Interstellar travel is difficult not just because space is big, but because space is big in a relativistic universe, and that is why the speed limit should not be heard as cosmic cruelty. It is better understood as a statement about what kind of universe we inhabit. Distance, delay, and causal order are woven together. When we reach for the stars, we are not merely confronting engineering weakness, we are confronting the architecture of spacetime. Those benchmarks matter for another reason, and that keeps this video honest. Human engineering can be extraordinary and still remain very far from the relativistic boundary. That gap does not make relativity abstract. It is precisely why relativity becomes the long-term map, rather than a near-term propulsion footnote. Now, spacecraft examples are emotionally powerful because they connect the topic to human ambition. We want to cross the solar system faster. We want to imagine missions to nearby stars. We want to know whether the cosmos is merely difficult or fundamentally resistant. And that is why Parker Solar Probe and similar records are worth mentioning. They give the audience something tangible. Numbers in the hundreds of thousands of miles per hour sound enormous because they are. Human engineering really is capable of extraordinary motion. But these examples must be used carefully. They are not explanations of relativity. They are scale-setting examples. If you overuse them, the topic can slip back into a weaker engineering frame, as though the whole issue was simply how many orders of magnitude of propulsion improvement remain. The stronger use of spacecraft benchmarks is to show that our intuitive idea of fast remains far inside the non-relativistic regime. Even spectacular engineering wins are still tiny fractions of c. That tells the audience something important. The boundary we are discussing is not the next practical milestone in aerospace. It belongs to a much deeper physical territory. And this is also why interstellar travel talk so often goes wrong. People imagine a straight line from today's rockets to tomorrow's near-light craft, as if the problem were one of persistence alone. Persistence matters, but only inside physical law. The closer a mission design moves toward relativistic speeds, the more the energy problem, shielding problem, and causal speed reality all become dominant. So spacecraft examples belong in the story for humility and perspective. They ground the subject. They should not be mistaken for the source of the rule. The comparison with the sound barrier is so common that it deserves a direct answer. The sound barrier once looked dramatic. Aircraft approached it, encountered major engineering problems, and for a time people spoke about it with a kind of reverence. Then aircraft exceeded it, and the phrase became a historical milestone rather than a fundamental limit. That history tempts people to ask whether light speed is just the same story, waiting for a future engineering breakthrough. But the comparison fails for a precise reason. The sound barrier is a property of how pressure waves propagate in a medium, combined with the aerodynamic behavior of objects moving through that medium. It is a serious engineering threshold, but not a universal causal boundary built into spacetime itself. An aircraft crossing Mach 1 does not overturn simultaneity, threaten causal order, or require the restructuring of space and time. It is just moving faster than sound in air. Crossing c in special relativity would be fundamentally different. It would not mean beating a difficult medium-specific threshold. It would mean crossing the invariant boundary that organizes causal propagation for all inertial observers in vacuum. And that is why the light speed limit is not just a harder sound barrier, it belongs to a different category entirely. Now, part of the reason this topic keeps returning in culture is that it collides with a very deep human desire. We do not merely want to move, we want to erase delay, we want remoteness not to matter. We want the stars to feel conquerable in the same way oceans and continents eventually became conquerable. The light speed limit frustrates that desire at a philosophical level, not just a technical one. It tells us that distance and delay are not accidental features waiting to be optimized away completely. They are linked to causal structure, and that can feel bleak if it is phrased badly. But there is a stronger way to hear it. The universe is not being cruel. It is revealing that the world has form. Some possibilities are wide open. Others are tightly constrained because they are entangled with the consistency of reality itself, and human progress has often consisted of discovering that a supposed limit was merely local, not fundamental. The reason the light speed topic is so enduring is that it asks whether this is one of the rare cases where the limit really is structural. Within special relativity, the answer is yes. That does not kill wonder, it deepens it. We are not merely creatures trying to build better engines. We are creatures trying to understand what kind of universe those engines live in. And relativity's answer is astonishingly elegant. The universe does not give us one universal present. It gives us one invariant causal structure. That trade is part of what makes the world coherent. And part of the emotional resistance comes from how naturally we inherit a Newtonian picture long before we learn any physics. We think in terms of landscapes, vehicles, and distances waiting to be conquered. Relativity does not merely say the landscape is larger than we hoped. It says the meaning of distance, delay, and access is different from the start. Now, in an ordinary intuitive picture, distance is just how much space lies between two places. Relativity adds a deeper layer. Distance is not only separation in space, it is separation in a world where influence takes time and where different observers partition space-time differently. That means remoteness is not a purely geometric inconvenience. It is tied to causal accessibility. Some places are not merely far in meters. They are far in a universe where the cone structure limits how quickly interaction can occur. And this is why astronomy feels the way it does. Looking farther away is also looking into the past. Messages take time. Light itself is not a transparent courier outside the world's structure. It is part of the structure. The finite speed of light is the reason distance and history become entangled in observation. So when we ask why the stars feel so unreachable, part of the answer is not merely that the numbers are large, it is that the numbers are large in a relativistic universe. One reason relativity can feel unbelievable is that daily life seems to contradict it. Cars add speed in the familiar way. Clocks on walls appear universal. People far apart casually speak as if now means the same thing for everyone. Nothing in ordinary experience feels like light cones and relativistic simultaneity. But that is not evidence against relativity. It is evidence that ordinary life occupies a very low-speed corner of the theory where relativistic corrections are tiny. Newtonian intuition works because it is an excellent approximation when velocities are small compared with c, and when the precision demanded is modest. This is an important perspective because it explains why the speed limit can seem artificial if introduced too suddenly. We grow up inside an approximation and mistake it for the fundamental picture. Relativity does not make the everyday world wrong. It shows why the everyday world is a simplified limit of a deeper structure. And that is also why the topic should not be narrated as though Einstein replaced common sense with nonsense. He replaced a local approximation with a more general framework that reduces to common sense under the conditions where common sense earned its reputation. Now, a strong explanation also has to clear away some bad intuitions. Now, the limit does not mean the universe is static or ungenerous. Relativity does not prevent extraordinary motion. Matter can move extremely close to c. Nature contains jets from black holes, cosmic rays with astonishing energies, and particles in accelerators moving so near the boundary that ordinary intuition becomes useless. The limit is not a ban on speed. It is a structural distinction between approaching the boundary and crossing it. And the limit does not mean light is always the fastest thing in every medium in every practical context. Light can move more slowly through matter because the signal is interacting with that material. That does not weaken the relativistic role of c as the invariant vacuum speed and causal benchmark. Confusing effective speeds in media with the deeper vacuum limit is a common source of bad explanations. And the limit does not mean time dilation is an illusion, nor does it mean time dilation is the root cause. It is part of the same framework. The right picture is not that clocks misbehave under stress. The right picture is that different inertial observers legitimately measure different time intervals, because their space-time descriptions differ, while preserving the same invariant structure. And the limit does not mean E equals mc squared explains everything on its own. That equation is part of the story, especially when discussing energetic cost, but it does not replace the geometry of space-time or the causal logic of light cones. And the limit does not mean our interest in advanced travel is pointless. There is a huge difference between impossible fantasies and ambitious work constrained by real physics. Relativity narrows the landscape. It does not erase it. Even without crossing c, time dilation, propulsion trade-offs, and long-duration mission design remain rich scientific and engineering territories. And most importantly, the limit does not mean the universe is arbitrary. In fact, it means the opposite. The same rule shows up everywhere because the universe is not arbitrary on this point. The speed limit is one expression of a deeper consistency. That consistency is what makes the subject beautiful. The speed limit is not sitting off to one side like an annoying policy memo from nature. It is entwined with the shape of space-time and the integrity of cause and effect. Any honest scientific discussion should leave a little room for humility. Physics is not scripture. Theories are accepted because they work, because evidence supports them, and because they organize reality well. If future physics were to revise our deepest picture, then our understanding of limits might also change in ways we do not yet foresee. But that humility should not be confused with vagueness. Within special relativity, and within the broader framework that has inherited and generalized its causal structure, the speed limit is not a loose guideline, it is central. So the disciplined position is this: we do not claim eternal metaphysical certainty. We do claim that the best tested relativistic description we have says c is the invariant causal speed, that massless propagation in vacuum occurs at c, that massive objects cannot be accelerated to c, and that superluminal causal influence would undermine relativistic causality. And that is already an extraordinarily strong conclusion. It is more than enough to answer the question this video set out to address, and perhaps there is something satisfying in that. We do not need to inflate the claim beyond what the theory supports. The real result is already deep. The speed limit exists not as a quirky add-on, but because the universe, as described by relativity, is built around an invariant causal structure, and there is always pressure in popular science to compress. That is fine, but compression has a danger. It can quietly reverse the logic. Now, for example, saying objects cannot reach light speed because time slows down is shorter than explaining invariant speed, simultaneity, and causal structure. But it gives the wrong causal hierarchy. Saying photons go at c because they are pure energy is shorter than discussing massless null propagation, but it is conceptually sloppy. Saying E equals mc squared proves the speed limit is shorter still, but it turns one support beam into the whole building. The reason to resist those shortcuts is not pedantry. It is that the full logic is actually more satisfying. Once the chain is in the right order, the topic becomes cleaner, not messier. The universe contains an invariant speed, space and time therefore reorganize. Causality therefore acquires a cone boundary. Massive and massless motion therefore separate into different classes. The energy wall near C therefore has a clear geometric context. Good explanation is not about stripping away structure until only slogans remain. It is about preserving the order of the structure while making it intelligible. It is tempting to hear all this and conclude that relativity mainly tells us no. No superluminal travel. No instant messaging across the stars. No simple escape from cosmic distance. But there is a better way to read it. Relativity tells us what kind of game we are playing. Once we know that, we can ask more intelligent questions. How close to C can we push probes, even if exact arrival is forbidden for massive objects? How do time dilation and energy cost reshape mission planning? What strategies become interesting once we accept long delays as part of the environment instead of as engineering defects? What kinds of civilizations could flourish while respecting causal structure, rather than fantasizing about ignoring it? And these are not small questions. They are what ambitious thinking looks like after reality has been described honestly. Physics does not shrink human imagination, it gives imagination a sharper map, and that may be the most useful final consequence of the speed limit. It forces ambition to mature, not into resignation, but into strategy, not into mysticism, but into understanding, and relativity changes many intuitions, but it does not change everything. Causes still precede effects for events that can actually influence one another. Engineering still matters, energy still matters, careful measurement still matters. What changes is the framework inside which those things must operate. And that is another reason the speed limit should not be heard as a rejection of practical science. It is an instruction about the deeper stage on which practical science happens. Build better probes, better accelerators, better clocks, better detectors, better theories. All of that remains meaningful. But do it inside the understanding that C is not merely a benchmark to chase. It is the invariant boundary shaping the causal world those instruments inhabit, and that is the final mental correction this topic asks of us. Stop imagining the universe as ordinary space and ordinary time plus one very fast thing called light. Start imagining it as space-time with a built-in causal structure, one that light in vacuum happens to reveal with unusual clarity. And once that correction is made, the limit stops feeling arbitrary. It begins to feel inevitable. Now, for human beings, the hardest part of this topic is not the math, it is the implication. We want the universe to be traversable in the same spirit that landscapes on Earth became traversable. We want enough intelligence and enough power to make all distance negotiable. And relativity answers with something more subtle. Distance is negotiable only within a world where causal structure remains intact. We can do extraordinary things, but not by tearing apart the order that lets events make sense. The light speed limit is therefore not just a challenge to our machinery. It is a reminder that the universe has a built-in grammar, and ambition has to become fluent in that grammar rather than trying to abolish it. And that is why this subject feels bigger than a number. It tells us what kind of reality we inhabit. At this point, we can finally bring the pieces together. The speed limit is not one isolated fact. It is not just a number attached to light. It is a chain of ideas that only makes sense when each part is placed in the right order. The universe contains an invariant speed, c. Every inertial observer measures that same speed for light in vacuum. Because of that, space and time cannot remain absolute in the old Newtonian sense. Simultaneity becomes relative. Once simultaneity is relative, causal order needs a stable boundary so that causes do not become effects for some observers. Light cones provide that boundary. Massless particles move on it. Massive objects remain inside it. And when massive objects are pushed closer and closer to that boundary, the required energy rises without limit, and that is the backbone of the subject. Worth holding the order carefully, because many shorter explanations quietly reverse it. They say objects cannot reach light speed because time slows down, or because photons have no mass, or because E equals mc squared makes the energy too large. Each of those statements touches part of the truth, but none of them is the whole structure. The deeper explanation begins earlier. It begins with the invariant speed built into spacetime. From there, the rest follows, and light in vacuum matters because it reveals that invariant speed. It is not simply the winner of a cosmic race. It is the messenger that moves along the causal boundary. Photons do not set the rule by being unusually fast. They show us the rule because massless propagation follows the null structure of spacetime, and massive objects are different. Their motion belongs to the time-like interior of the light cone. They can be accelerated. They can move extremely fast. In principle, they can approach C closer and closer, but they do not become light-like while remaining massive. Their world lines stay inside the cone, and that is why the energy wall is not just a fuel problem. Near C, added energy no longer turns into speed in the everyday way. The object's energy and momentum continue to rise, but the remaining gap to C becomes harder and harder to close. The limit is not enforced by a physical wall. It is enforced by the relativistic relationship between energy, momentum, velocity, and the geometry of spacetime. And this also explains why faster-than-light influence is so dangerous to the theory. The issue is not simply that it would be very fast. The issue is that it would connect events outside the light cone, where different observers can disagree about time order. For disconnected events, that disagreement is harmless. For a real signal or cause-effect link, it is not. Once influence moves outside the cone, causal order can become unstable. So the cleanest version is this: the speed limit exists because the universe has an invariant causal speed. Preserving that speed forces space and time to behave differently from everyday intuition. Simultaneity becomes relative. Light cones become the geometry of possible influence. Massless particles move on the cone boundary. Massive objects remain inside it. Faster-than-light signaling would threaten causal order, and pushing massive matter toward the boundary demands unbounded energy. And that is the chain. And once it is seen in that order, several confusions begin to dissolve. The question is not why light is so special that nothing can beat it. The better question is why spacetime has an invariant causal speed that light in vacuum happens to trace. The question is not why engines are too weak. The better question is why a massive object cannot move from a time-like path onto a null one by ordinary acceleration. The question is not whether time dilation is a strange trick that blocks motion. The better question is why space and time must be measured differently by different observers if C is to remain the same for all of them. And the question is not whether one famous equation explains everything. E equals mc squared belongs to the story, but it does not replace the story. The full explanation needs space-time geometry, causal order, massless and massive motion, and relativistic energy together. And this is why the light speed limit feels so different from ordinary barriers. A mountain can be crossed, a sound barrier can be broken, a fuel shortage can be solved. A material limit can sometimes be overcome by new engineering. Those are serious problems, but they belong to the world of better tools and better technique. The light speed limit belongs to a deeper category. It is not a statement about the weakness of current machines. It is a statement about the kind of spacetime those machines exist inside. That does not mean ambition is pointless. It means ambition has to be aimed at the right problem. If we want faster spacecraft, propulsion matters. If we want long missions, shielding matters. If we want interstellar probes, energy, dust impacts, communication delay, navigation, and autonomy all matter. But none of those challenges remove the underlying causal structure. They operate within it, and that is the mature version of the original question. Not simply, why are our rockets too slow? But, what does it mean for us to live in a universe where causality itself has a speed? And the answer, the one we have been building toward, is that distance, delay, motion, and time are not separate inconveniences. In relativity, they are connected. A distant star is not merely far away. It is far away in a universe where influence takes time to travel, where observers do not share one universal present, and where massive objects cannot outrun the causal boundary. And that is why the right image is not a rocket pushing against a speedometer. The right image is a light cone. At every event, we find a structure of possible influence. The future cone marks what can be affected. The past cone marks what could have contributed. The boundary is traced by light in vacuum and other massless propagation. The interior belongs to massive motion. Outside the cone are events that cannot be causally reached within that interval by ordinary means, and different observers may slice that structure differently into space and time. They may disagree about simultaneity for distant events. They may assign different durations and distances, but the cone remains the organizing structure underneath those descriptions, and that is the real strength of relativity. It gives up the old comfort of one universal now, but it replaces it with something more precise, an invariant causal architecture. And this is also why the limit is not arbitrary. If c were just the speed of one object, the rule would feel like a strange coincidence. But c is not merely the speed of light. It is the invariant speed that holds the structure together. Light reveals it. Causality depends on it. Massive motion respects it. Energy costs expose it. And once that is clear, the subject becomes less like a prohibition and more like a map. And it tells us why photons move the way they do. And it tells us why matter can approach c but not reach it. And it tells us why particle accelerators behave as they do. And it tells us why communication across space is delayed. And it tells us why astronomy is always looking into the past. And it tells us why any serious future of space travel has to think not just about distance, but about time, causality, and the cost of approaching the boundary. So the chain is not an ending yet. It is the framework for everything that follows. The remaining question is what this framework means for us, for actual travel, observation, and human ambition. Relativity does not simply close the door, it changes the shape of the corridor. It tells us that even lawful journeys near C would not behave like faster versions of ordinary travel. They would involve different elapsed times, different relationships to home, unavoidable communication delays, and a universe that cannot be made instantly present. That is where the practical meaning of the limit begins. Now, one reason this subject remains emotionally charged is that relativity seems to offer two opposite feelings at once. On one hand, it tells us the stars are stubbornly hard to reach. On the other hand, it tells us that for travelers moving close enough to see, the experienced duration of a journey can become much shorter than the duration measured by people who stayed behind. And that duality matters because it shows how easy it is to misunderstand what relativity does and does not permit. If a spacecraft could one day travel at speeds extremely close to C, the crew would not somehow see the universal speed limit disappear. They would still live inside the same causal structure as everyone else. They would still remain below C if they were massive travelers. Yet their proper time, the time experienced along their own world line, could be dramatically less than the coordinate time measured in the frame of Earth or the destination star. And this is one of the places where relativity can sound almost like a loophole. A journey of many light years might be many years or decades in one frame, while the crew ages much less. That is real physics. It is not a trick. But it is not a violation of the speed limit either. The reason is simple once the structure is clear. Relativity does not say all observers must agree on elapsed durations between separated events. It says they must agree on the underlying causal structure and on the invariant speed c. Different frames can assign different combinations of distance and time, while preserving that structure. So imagine a crew heading toward a star system many light years away at a speed extremely close to C. From Earth's frame, the star remains many light years distant, and the travel time remains correspondingly long. From the traveler's perspective, the distance along the direction of motion is length contracted, and their onboard clocks accumulate less proper time than Earth clocks do over the full mission. Nothing about that picture crosses C. Nothing about it allows an ordinary massive spacecraft to outrun light. The ship still moves along a time-like world line, always inside the cone. But the relationship between distance traveled and time experienced is no longer the simple Newtonian one daily intuition expects. And this is important because it rescues the subject from two opposite mistakes. The first mistake says relativity makes interstellar travel impossible in every meaningful sense. The second says time dilation is basically a free ticket to bypass the light speed limit. Neither is right. Relativity does make interstellar civilization difficult. It makes it expensive, delayed, and asymmetrical across frames. But it does not make all large journeys equally hopeless from the traveler's own perspective. If enough energy could be supplied, a near-K mission could be survivable in onboard time, even while the outside world experiences far more elapsed time. And that trade is profound. It means the limiting factor is not only whether humans or machines could endure the trip personally, it is also what kind of relationship they would still have with the civilization that launched them. A crew might reach a distant destination within a lifetime of subjective experience while returning, if return were possible, to a profoundly changed home, and this makes relativity feel less like a simple travel ban and more like a redefinition of what travel means. On Earth, long-distance travel usually preserves social continuity. A long flight or sea voyage still returns you to almost the same historical moment you left. Near sea, that assumption breaks. Motion and elapsed time separate in ways that turn distance into both a spatial and historical divide. The speed limit, therefore, does not only set mission durations, it changes the social geometry of exploration, and it also changes how we should think about ambition. There is a tendency in futuristic discussions to rank possibilities in only one dimension. Can we get there or not? Relativity forces a better question. Get there for whom, in how much proper time, after how much external time, with what energy cost, and under what communication delay? And those are not bureaucratic details added after the physics. They are the physics translated into lived consequence. And here again the cone picture helps. Even a ship moving arbitrarily close to sea still carries its own cone-bound future with it. Messages to and from home still travel causally, never instantly. Coordination across distance remains slow. The crew does not escape the causal world. They merely navigate a part of it where the conversion between experience duration and frame-assigned duration becomes extreme. And that is why near-light travel is not a contradiction of relativity, but one of its most human implications. The theory does not merely tell us what cannot happen, it tells us what a successful but lawful confrontation with cosmic distance would actually look like. And what it looks like is not simple conquest. It looks like accepting that the road to the stars, even in the most optimistic, physically lawful version, is also a road through different amounts of time. Now, at this point, many viewers naturally reach for the famous escape hatches. What about wormholes? What about warp drives? What about the expansion of space carrying galaxies apart faster than light? Do these ideas mean the limit is not really a limit after all? And these are fair questions, but they belong to a different layer of discussion than the one we set out to answer here. The core question here is why a massive object moving locally through spacetime cannot simply keep accelerating past c. Special relativity gives a very strong answer to that local question. Locally, in ordinary inertial motion through spacetime, c is the invariant causal speed. Massive objects remain timelike. Massless propagation is null. Superluminal influence destabilizes causality, and the energy cost of pushing massive matter toward the boundary rises without limit. Speculative concepts like wormholes or Alcubierre-style warp metrics do not overturn that local structure in any simple way. They attempt, at least on paper, to change the global geometry through which motion occurs, rather than to accelerate a massive object through its local light cone in the ordinary sense. And that distinction matters enormously. If a wormhole existed and were traversable, the traveler would not be winning a local race against light through ordinary flat spacetime. The idea would instead be that spacetime geometry itself provides a shortened path between distant regions. Likewise, a warp metric is not usually described as a ship locally outrunning light in its neighborhood. It is described as a distortion of spacetime geometry in which the ship remains locally subluminal while the geometry evolves around it. Now, whether such constructions are physically realizable is a much harder question, and the honest answer today is that they remain speculative, burdened by severe theoretical problems, exotic energy requirements, stability issues, and unclear compatibility with a complete quantum theory of gravity. So these ideas are not clean loopholes to the argument we have built. If anything, they reinforce how strong the ordinary limit is. We only arrive at such extreme proposals because simply accelerating matter through c is not what relativity allows. The cosmic expansion example is similar. Distant galaxies can recede from one another faster than c in an expanding universe. But this does not mean a local rocket has beaten the light speed limit. General relativity allows spacetime itself to evolve on large scales. The recession of distant galaxies in cosmology is not the same thing as local superluminal travel or superluminal signaling through a local inertial frame. That distinction is often lost in casual conversation. Someone hears that the universe expands faster than light in some sense and assumes special relativity has already been broken by observation. But it has not. The local causal structure remains intact. Nearby physics still respects the invariant speed. The cosmological story involves curved, dynamical spacetime, not an ordinary object overtaking its local light cone. This is one more reason good wording matters. The phrase "nothing can go faster than light" is useful only if the context is remembered. The relevant claim concerns local propagation, local motion, local causal structure, and the invariant role of c in relativity. Once people start mixing local special relativistic motion with global cosmological geometry, confusion multiplies fast, and there is also a deeper point hiding here. Even the most imaginative loopholes people discuss are not attempts to prove c irrelevant. They are attempts to work around the consequences of a universe in which c matters profoundly. The very need for such detours is evidence of how central the ordinary limit is. So if one day physics discovers a consistent, experimentally supported route to extraordinary spacetime engineering, that would not erase the explanatory chain we have followed here. It would modify the map at a deeper level. But the current question, the one grounded in tested relativity, would still have been answered correctly on its own terms. Why can a massive object not simply accelerate past light speed through ordinary spacetime? Because the universe we measure does not permit that local crossing without sacrificing the relativistic structure that gives the theory its coherence. And that is the question we set out to answer here. Speculative geometry can be interesting. It is just not the same question. The speed limit can sound abstract until you remember how much of astronomy is really the study of delayed information. When we look at the moon, we do not see it as it is in some universal present. We see it about 1.3 seconds in the past. For the Sun, the delay is a little over 8 minutes. For the nearest stars, it is years. For galaxies, millions or billions of years. Astronomy does not merely suffer from finite light speed as an inconvenience. Astronomy is built out of it. That fact is easy to say and easy to underestimate. The sky looks simultaneous. It feels like a dome of things existing together right now. But the deeper truth is harsher and more interesting. The universe reaches us in layered slices of history because information takes time to cross space and because the speed of causal propagation is finite. This has practical consequences even close to home. Communication with spacecraft is never real-time once the distances grow. Commands to Mars take minutes each way depending on orbital geometry. Outer planet missions live on patience. A probe near Pluto cannot be flown like a drone over a nearby field. The finite signal speed is not a design flaw in radio hardware. It is the causal structure of the solar system expressing itself operationally. The same logic scales upward. If a civilization were spread across many star systems, it would not function like a globally synchronized nation-state. It would function more like a network of causally delayed communities, each acting partly on local knowledge and older information from elsewhere. The light speed limit would not simply slow their emails. It would shape politics, memory, coordination, and perhaps even identity. That may sound like a sociological detour, but it is really the same physics seen at a different scale. A finite causal speed means the universe does not permit instantaneous coherence across arbitrarily large distances. It permits only layered, delayed, cone-limited interaction, and astronomy also reminds us that the speed limit is generous enough to make science possible. Because light carries information at sea, the universe is not causally sealed into isolated local bubbles. We do learn from distant events. Supernovae, quasars, gravitational phenomena, and ancient cosmic light all reach us eventually. The limit does not make knowledge impossible. It makes knowledge historical. And that is a subtle but beautiful point. We know the universe by receiving its past. The same finite speed that frustrates the fantasy of instant travel is the speed that lets distant reality become observable at all. And because that is true, astronomy becomes one of the most emotionally persuasive confirmations of relativity's worldview. The night sky does not present a universal now. It presents a visible archive sorted by causal delay. Distance and time are entangled in observation because C is finite and invariant. This is another place where the light cone is more than a teaching diagram. Every telescope is, in a sense, an instrument for sampling our past light cone. It gathers signals that had enough time to reach here, and only those signals. We never observe the universe from outside causal structure. We observe within it, and that is why the speed limit changes the meaning of remoteness. A galaxy is not only far away, it is far away in a universe where seeing it already means seeing ancient light. A probe is not only distant, it is distant in a universe where command and response must cross finite intervals. A future interstellar society would not only be spread out, it would be spread out in time as well as in space. And once you internalize that, the limit stops looking like an isolated law. It starts looking like the quiet organizer of cosmic experience. And that is perhaps the most elegant practical consequence of all. The same sea that constrains movement also makes the universe legible as history. Now the full answer can be stated one last time, but with all the weight of the chain behind it. Now, light speed is the limit not because photons won a cosmic race, and not because engineers have not yet found the right fuel. It is the limit because relativity describes a universe with an invariant causal speed. Once that speed is the same for all inertial observers, space and time cannot remain absolute in the Newtonian sense. Simultaneity becomes relative. Light cones define the boundary between events that can influence one another and events that cannot. Massless particles propagate on that null boundary. Massive objects remain within the time-like interior. Faster than light signaling would destabilize causal order, and pushing massive matter ever closer to the boundary drives the required energy upward without limit, and everything else follows from that. And it explains why photons are not exceptions but traces of the rule. It explains why particle accelerators approach C without crossing it. It explains why muons survive to the ground, why GPS needs relativistic corrections, why spacecraft communication carries unavoidable delay, why astronomy is a study of the past, and why interstellar travel, even in its most ambitious lawful form, is inseparable from time dilation and causal separation. And it also explains why the topic should feel bigger than a number. The important fact is not merely that C is about 300,000 kilometers per second. The important fact is that C marks the finite speed at which causal influence propagates in the relativistic structure we actually measure. And that is why the right mental picture is not ordinary space plus one very fast phenomenon called light. The right picture is space-time with a built-in causal grammar, one that light in vacuum reveals with unusual clarity. And once that grammar is understood, the limit stops feeling like an arbitrary refusal. It starts to feel like the natural expression of what this universe is. So the final plain language answer is the calmest one. Why is light speed the limit? Because reality appears to be built so that cause itself spreads at a finite invariant speed, and every massive thing we make has to live inside that structure. And there is one last practical misunderstanding worth clearing away. When people hear that enormous energy would be needed for relativistic travel, they often still imagine an ordinary engineering scale-up. If present rockets are too weak, perhaps a future civilization simply builds a much larger power source and continues along the same basic path. But the relativistic energy problem is not just a bigger version of ordinary propulsion. It changes character as velocity rises. Now at everyday speeds, energy and velocity feel closely coupled. More energy usually means noticeably more speed for us. In the relativistic regime, especially as v approaches c, more energy increasingly means more energy rather than much more speed. The object's momentum and total energy continue to rise, but the remaining gap to c becomes ever more stubborn. And that distinction matters because it tells us the challenge is not merely one of civilizational patience. It is built into the functional shape of the equations. A society with far better power systems could absolutely do things we cannot. It could push probes to fractions of c that remain far beyond current engineering. It could change the practical scale of interplanetary and perhaps interstellar activity. But even that success would still occur on the same side of the asymptote. And this is why particle accelerators are such honest teachers. They are machines specifically designed to pour enormous energy into particles. And what do they show? Not a crack in the limit, but a vivid demonstration of its structure. The particles get astonishingly close to c, while the pattern of diminishing speed gains and soaring energy cost becomes exactly the story relativity predicts. And for macroscopic spacecraft, the problem is harsher still, because the energy must be supplied not just to individual particles, but to an enormous organized payload with shielding, guidance, communication capability, and some way of surviving collisions with dust and gas at relativistic speeds. The speed limit is therefore not the only challenge we face. It sits inside a larger practical wall made of propulsion, heat, materials, radiation, impact risk, and mission economics. Yet even here the conceptual hierarchy matters, and we should not lose it. Those engineering obstacles are not the fundamental reasons c is the limit. They are severe consequences layered on top of a deeper rule. We could imagine astonishing advances in materials and power, and the relativistic boundary would still remain exactly what it is. Now, a useful way to phrase this is that relativity does not merely make the bill expensive. It changes what the bill is being charged for. Near c, you are not simply paying to go faster on an otherwise ordinary road. You are paying to push time-like motion ever closer to the null structure of space-time itself. And that is why no amount of motivational language about future innovation really touches the core issue. Innovation matters, better propulsion matters, better energy storage matters. We are not dismissing any of that. But the shape of the challenge is still dictated by relativity, not by optimism. So, seen this way, the speed limit becomes strangely clarifying. It tells us which dreams belong to engineering extrapolation, and which would require a deeper change in physical law or geometry. It lets ambition become more exact, and that is valuable to us, genuinely useful for us. Physics is most helpful not when it flatters our intuitions, but when it tells us exactly what kind of problem we are trying to solve. If there is a quiet emotional lesson in all of this, it is that the universe is neither mocking our ambition nor surrendering to it. It is answering in a different language. Now, human beings evolved in a world where space and time felt separate, where causes looked local and immediate, and where long-distance travel meant crossing terrain rather than negotiating causal structure. So, of course, the relativistic universe feels counterintuitive. It was never going to look like common sense written at a larger scale. But once the logic is understood, the result is not cold. In a strange way, it is more intimate. It tells us that every message, every observation, every journey, and every measurement unfolds inside one coherent architecture. The same rule that limits spacecraft also lets us interpret the night sky. The same finite causal speed that frustrates instant contact also makes sequence, explanation, and history possible. That means the speed limit is not simply a door closing. It is also a sign that the universe is lawfully structured enough to be understood, and we can discover its invariance. We can learn how clocks disagree without reality becoming chaos. We can describe why photons live on a boundary and matter does not. We can measure the consequences, build technologies around them, and orient our ambitions accordingly. And that is a more durable kind of wonder than the fantasy that all limits are temporary embarrassments. Some limits teach us less about the defeat than about the architecture of the game, and this particular limit teaches something unusually deep. It tells us that causality is not an afterthought added onto a stage of absolute space and absolute time. It is built into the stage itself. The universe is not first a giant container and only later a network of influences. It is a causal structure from the start. And that is why the answer to the title question cannot be a single slogan. Light speed is the limit because relativity has reorganized the world more profoundly than the slogan suggests. It has tied distance to delay, motion to elapsed time, observation to history, and travel to the geometry of possibility. And once that is seen clearly, the light speed limit stops feeling like a rule we might someday shame the universe into relaxing. It starts to feel like one of the deepest clues we have about what kind of place the universe is. Imagine a star system 4 light-years away. In ordinary language, that sounds like a fixed statement about distance alone. But relativity immediately turns it into several linked questions. 4 light-years according to which frame? How much time passes on Earth before arrival? How much proper time passes for the travelers? How much energy was required to get close to C in the first place? How much delay affects every message sent back home? And could any part of the mission outrun the cone structure that keeps cause and effect coherent? The core answers come quickly. A massive ship cannot simply accelerate through C and arrive in less than 4 years, according to Earth, by locally outrunning light. The ship remains time-like. The signals it sends remain causal. The outside world still sees a journey bounded by the finite structure of space-time, yet on-board time might be significantly less if the ship moves close enough to C, because relativity does not preserve one universal elapsed time for all observers. That one example contains almost the whole documentary. C is invariant. Simultaneity is not absolute. Light cones matter. Massive objects do not become light-like by trying harder. Communication delay remains fundamental. Energy cost becomes punishing near the boundary, and the result is not impossibility in every sense, but travel reshaped by a universe whose causal order has a finite speed. That is the carry-away picture, not a magical wall in space, not a mere engineering inconvenience, not a slogan about photons being unusually talented, just a relativistic universe in which cause spreads finitely. Measurement reorganizes around that fact, and every ambitious journey has to respect it. And this is why the light speed limit belongs in the category of explanation, not discouragement. It tells us what sort of universe we actually inhabit. Once we know that, the right response is not to pretend the structure is optional. The right response is to think more clearly inside it, to build more honestly inside it, and to let our ambitions grow up inside the cone rather than outside it. That final adjustment may be the real gift of relativity. It replaces a childish picture of unlimited speed with a sharper picture of lawful possibility. And in science, lawful possibility is always more valuable than fantasy, because it tells us where understanding can still become action. So the calmest possible conclusion is also the strongest one. We live in a universe where there is a finite speed at which cause can spread, and light in vacuum reveals that speed. Matter remains within it. Our instruments confirm it. Our technologies already depend on it, and our future will have to think inside it. Now, light speed is the limit because the universe has a finite causal grammar. And every real experiment, every real clock, every real message, and every real journey we know has to speak that grammar. That is the answer. For now, it stands.